All right, this is lesson 1.3 in our Pre-Calc 11 class. Unit 1 is called Radicals and Rational Exponents. Lesson 3 is called Simplifying Radicals. In the last lesson, we looked at simplifying radicals geometrically. So for any form of math, looking at the geometric representation is usually the best place to understand it conceptually. And then we jump to algebra, where we take those and we abstract those ideas and extend them beyond ways that we can represent them geometrically, which is exactly what we're going to do right now. So in this lesson, we're going to talk about how do I simplify radicals with variables, and how do I simplify radicals other than just square roots. So far we looked at square roots. Now we're going to look at higher order roots. Straight into examples. So we have a couple examples here. Example A is the square root of 36x to the power of 7, y to the power of 2. So we're looking for the biggest, let's see here. So let's say when we say simplify, we're saying let's make the radicand, the thing inside the radical, as small as possible. Or to say that a different way, we're trying to pull as much value out of the radical symbol as possible. And we're going to do that by finding perfect squares. So we have 36 as our numerical base inside this radical. 36 we know is a perfect square. It's 6 times 6. So the square root of 36 is just 6. So I'm going to take the 36 outside of the radical and put 6 outside. 36 goes away from inside and 6 goes outside. And so similarly with the x's, we're looking for perfect squares. 6 times 6 is 36, so 6 goes out. And so now with the x's, if we take two x's that are being multiplied, x times x is x squared. So if we abstract this, we can think, okay, x squared is a perfect square. So x times x goes out of the radical, and a singular x goes out of the radical in its place. So if we break up x to the power of 7, that's 1, 2, 3 pairs of x's, and then a 7th x left over. So the 3 pairs of x's are each going to be an x outside of the radical. The 7th x is going to be the x that stays inside the radical. Similarly, by that logic, y squared is also a perfect square. Y times y is y squared. So y squared goes away from inside the radical, and we put a single y outside the radical to represent that pair. So our final simplified answer is 6x to the power of 3y times the square root of x. And so if we try to connect this back to our geometric representation, it's probably going to sound ludicrous, but we're building a square, and the number of blocks on one side of this square is 6 times x to the power of 3 times y. Like I said, it sounds ludicrous. And the amount of space, the area of each one of those blocks is an area of x. There you go. So, yeah. Anyways, example B. We have x squared outside of the box. Outside of the radical. Inside the radical, we have 16 times x to the power of 3 times y to the power of 6. If we break that down in pairs, we've got a pair of 4s, we've got a pair of x's, we have a leftover x, and we have 3 pairs of y's. A pair of 4s is 1 4 outside of the radical. A pair of x's is 1 x outside. The remaining x is an x inside. And the 3 pairs of y's makes 3 y's, or y to the power of 3 outside of the radical. And now that we have simplified the radical, we also had that x squared in the beginning expression, and we added another x outside that we took out of the radical. So now we're going to combine like terms. X squared times a third x is going to be x to the power of 3. So our final simplified expression for example B is going to be 4x to the power of 3 times y to the power of 3 times the square root of x. There you go. Those procedures we're using are going to be the same throughout these next few slides. What's going to be different is the nth root, the root we're doing. So we're going to look at that. In this case, we have third root radicals, or cube roots. And so we notice in the square root, in the radical symbol, we have a little 3 up in there. It's not an exponent, it's a root number. They're related to exponents, but we're not going to get to that just yet. Right now, this is saying the third root of 27x to the power of 24. So in square roots, we're looking for 2 of a kind inside the radical. With third roots, we're looking for 3 of a kind. So 27 is 3 times 3 times 3. Well, that's 3 of a kind. That's 3 3s. And then we have 24 x's. So if I group those x's into groups of 3, we have 1, 2, 3, 4, 5, 6, 7, 8 groups of 3 x's. 8 groups of 3, or I could say 24 divided by 3, which gives us 8. So we're going to have 1 3 come out of the radical. There's 8 triplets of x's, so 8 x's are going to be outside the radical. So x to the power of 8. My apologies, there should be an x right here, and one of my lines disappeared. So 3x to the power of 8 should be the final answer. For example B, we're doing the third root of 16y to the power of 14. 16, if I factor that down, that's 2 times 2 times 2 times 2. And then, so we'll have 1 triplet of 2, and we'll have 1 extra 2. The triplet of 2 will become a 2 outside the radical. The lonely 2 will stay inside the radical. We'll break the y's into groups of 3. So we've got 3 y's, 6, 9, 12, 12 y's, plus 2 extra, for a total of 14 y's. That makes, as far as triplets go, that's 1, 2, 3, 4 triplets of y's. Ooh, there's a typo in my thing. Man, this 5 should be a 4 right here. I think I've got middle schoolers outside my door yelling. Fantastic, it must be Friday. Hashtag Flamingo Friday, join the flock. Anyways, yeah, so this should be y to the power of 4, because there's 4 triplets up here. So please ignore this 5, it should be a 4. We have 2 extra y's, so y squared is going to stay inside of our radical. So our final answer will be 2 times y to the power of 4 times the third root of 2y squared. All right, so we can simplify third roots, we can simplify radicals of any roots. Any number we put up there will just be the number of the number in a set that we're looking for when we pull out of a radical. So instead of saying any radical, we could say a radical to the nth root, n standing for any number we want it to. In example A, it stands for 8. In example B, stands for 6. 8th root and 6th root. So in example A, we have 45 x's inside the radical, and it's an 8th root radical. So we're looking for groups of 8. Well, I know that 8 times 5 is 45, so we've got 8, 16, 24, 32, 40 8s right there. We have 40 x's, and we have 5 x's left over. So each group of 8 x's will be 1 x outside of the radical, so x to the power of 5. And the remaining x's will stay inside the radical. So this x to the power of 5 is right here. So x to the power of 5 times the 8th root of x to the power of 5 is our fully simplified expression. Next one, we have the 6th root of 4 times x to the power of 18. 4 is a pair of 2's. 18 x's is 3 6 of kinds. And I like 6 of a kind because we're doing 6th root. So the 2's, there's not 6 of a kind in the 2's, so it's going to stay as a 4 inside the root. The 3 6 of a kinds for x's are going to come out, so we have x to the power of 3. 1 x for each 6th of them. So x to the power of 3 times the 6th root of 4 is the final simplified expression in there. Alright, last line. So now we're working with nth roots, but a little more complicated, only in that we've got more variables going on. And then also in example C, we got a negative. So let's break these down. Example A, we're doing a 4th root, so 4 of a kind. 81 is 4 3's, so we pull a 3 out. 8 x's is 2 pairs, so x to the power of 2. 18y's is 4 sets with 2 left over. So 4 sets means we have y to the power of 4 on the outside of the radical, and the y to the power of 2 stays inside. Here's our final expression there. Example B, 216 is 4 4s being multiplied. So 3 of them make a set that goes outside. The remaining 4 stays inside the radical. X to the power of 3 is 1 set with 1 left over. So we have 1x out for the set, and 1x inside the radical for the leftover. We have 11 z's, or as I call them z's because I'm an American, you probably call them z's. We have 11 z's. That's 3 sets of 3 and 2 left over. 3 sets of 3 means we have z to the power of 3 on the outside of a radical, and the 2 z's left stay inside the radical. So here's our final expression there, fully simplified. And again, simplify means we make the radicand, or the thing inside the radical, as small as possible. We pull as much out as we can, as much perfect squares out as we can. All right, takeaways. We can feel our radical powers getting stronger. My slides didn't work in class, so I didn't get to make this joke. So please, at home, laugh while you're watching this video. It makes me feel better about myself. Also, hopefully, you will be, as you work through some example problems on Delta Math and you look through the slides, you will find that you're actually getting more confidence in working with radicals. Hopefully, as you try more and more practice problems, it gets easier and easier as you go. Of course, it's going to get harder and harder because I'll throw more stuff at you, but this means your head's getting bigger because you're getting smarter.